Hi, good morning to Dr. Halim and fellow friends. My name is Yong Sing from School of Chemical Engineering. We will be presenting the topic regarding of active galactic nuclei AGN. So before this, I would like to introduce my group member, which is James Law, also from Chemical Engineering courses. So basically, we will be presenting about some introduction and history, and what is radiolog AGN, and some classification of radiolog galaxy, and lastly, a unified model of log radio AGN. So, for introduction, most of the galaxies we observe are considered as a normal. We inhabit in a normal galaxy, which called Milky Way. When you observe a normal galaxy, most of the light comes from a star and visible wavelength, and it is evenly distributed throughout the galaxy. But if you look at some galaxy, you will see intense light coming from their nuclei, and these are called active galaxy. Active galaxy emit up 1,000 times more energy than normal galaxy, but most of this energy released not in visible light, but other wavelength from radio waves until the gamma rays. This type of galaxy represent a very small percentage of all galaxies we have detected so far. There are four types of active galaxy, which including the Seyfert galaxies, quasar, blazar, and radio galaxy. This imaginative output of the active galaxy is driven by a supermassive black hole at their center. The discovery of the active galaxy nuclei was begun by Fate in early 20th century. Initially, Fate wanted to test the claim that the spiral nebulae show a continuous spectrum consistent with a collection of stars. One of the most significant observations in this case is the NGC 1068. He observed that the spectrum is showing a bright and absorption lines. Similarly, the Op spectrum of this NGC 1068 was seen by Westo Salifer and Edwin Hubble in 1913 at Lowell Observatory. Later in 1943, Carl Seyfert had identified 6 galaxies with strong and broad emission lines coming from a compact, bright nucleus, and now so-called those as Seyfert galaxy. Later in 1950, the first radio telescope was found, fan galaxy at a location of intense radio emission, and these were adopted as radio galaxies. So the real breakthrough came on the 1963 as the Smith was pondering the spectrum of the quasar of 3C273 and obtained a ratio of 0.158. He realized that the starlight radio source of 3C273 is the nuclear region of the galaxy. Such radio sources form a new class of the AGN and are named as quasar. In 1960, the idea of accretion matter onto a supermassive black hole is proposed to explain the behavior of AGN phenomenon by several astrophysicists. Martin Rees suggested that the source of radiation from the AGN is an accreting supermassive black hole lying at the center of the AGN in 1984, and so what we know as now. So yeah, that's all for the history, and we will talk about some radiolog AGN. Radiolog AGN often powered by a central astronomical object, so we call the supermassive black hole. The main feature that separates the AGN with the normal galaxy is the wider spectral range in the broadband continuous emission. The AGN can often power output of 10 to the power 41 watt within a relatively small region. This enormous amount of energy in a tiny region hint that its power source is not just the simple nuclear fusion. Radiolog AGN can be defined as the astronomical object with the luminosity greater than 10 to the power 23 watt per hertz. This radiolog makes the minority of 10% of all AGN observed so far. So we come to how to classify the radiolog galaxies that we observed so far. The obvious characteristic of the radiolog AGN is the large double loop structure. Based on this structure, radiolog can be classified into FR2, which has bright edges and hotspot, and FR1, which has light, bright, and outer edges. Essentially, two powerful jets of hot gas are being emitted. The radiologs form because these jets from a compact object are stopped by the intergalactic gases, where the hotspots of the radiation form. The energy at this hotspot flow back to form an evacuated cavity. These radiolobes contain fewer high-energy electrons compared to the jet of hot gas. Therefore, the radiolobes have a steeper radio spectrum, so it is best seen at lower radio frequency. So these are the examples of the FR1 and FR2 radio galaxy, which show at left and right respectively. Lastly, the radiolog agent can be further classified based on their optical spectral lines. The broad radio line galaxy BLRG exhibit both broad and narrow lines with a strong continuum emission, which dominated by FR2. Narrow line galaxy NLRG exhibit only narrow lines with a weak continuum emission, mostly FR1. And the weak line radio galaxies WLRG are dominated by a starlight of an elliptical galaxy with only one or two weak lines with a typical stellar absorption. So that's all for my sharing. So I will pass the floor to James to further explain about the unified model of Radiolog Engine. Thank you.
Thank you, Yongxin, for the explanation of AGN classification. As Yongxin discussed and explained, there are many different types of classification on AGN that can be observed by astronomers. A question that one might ponder: is this different astronomical objects altogether, or are they all just the same thing? Indeed, we can unify all these classes of AGN into one concept. This is known as the unified models of radiolog AGN. In this unified model of radiolog AGN, there are three main defining characteristics. First, we must have a supermassive black hole core in the middle. Next is the accretion disk, where infalling materials from interstellar and intercluster medium. Third is the relativistic jets caused by the generated magnetic field generated by the spinning accretion disk and black hole. There are two main different types of unified model AGN that is based on their luminosity or energy output: the radiative mode AGN and the kinetic mode AGN. First, let us talk about the radiative mode AGN. Take a look at this graph. Indeed, there are still three defining features of AGN that were discussed before: the black hole core, the accretion disk, and the relativistic jets. The cause of these different classes of AGN is because we have a very different view angle with respect to our line of sight for every AGN possible. So, if it is viewed directly towards the relativistic jets, we will have a very bright continuum emitters up to gamma rays. So this we will classify as flat spectrum radio quasars, FSRQ. If the AGN was viewed between the jet and the disk, we will call that broadline radio galaxy, BLRG, because there are broadline widths that we can observe. So the broadline widths implies that the clouds in that area are moving fast. Last but not least, narrow line radio galaxy would be observed if the AGN was viewed directly towards the dusty torus and the accretion disk. It will exhibit a very narrow line, and the photo fields are collimated by the dusty torus. Second, we have the kinetic mode AGN. So kinetic mode AGN has a physically thicker but optically thin accretion disk. So you might wonder, why is it the accretion disks are thicker in this kinetic mode AGN because the accretion rate or accretion spinning rate in the kinetic mode AGN is much slower than the radiative mode AGN. So it cannot maintain the flat accretion disk because it doesn't move very fast. So in this kinetic mode, in many viewed angle, you will actually just see a weak line radio galaxy if it's a kinetic mode AGN. Unlike radiative mode AGN, it can have a variety of AGN classes depending on the view angle. So what are the difference between kinetic and radiative AGN? So first, radiative AGN is radio louder than kinetic AGN. This means that radiative AGN has higher luminosity in radio waves compared to kinetic AGN. Thus, radiative AGN has a very high energy output compared to kinetic AGN. Radiative AGN also has a higher and faster accretion rate compared to kinetic AGN. So this is reflected by the radiative AGN has a flatter accretion disk, while kinetic mode AGN would have a physically thicker accretion disk. Third, the energy transfer in radiative mode is dominated by the radiation of the accretion disk. It's because radiative mode AGN has a very fast accretion rate, so it would release energy through the radiation around the accretion disk, while the energy transfer in kinetic mode are dominated by those relativistic effects instead of the accretion disk due to slower accretion rate. Last but not least, radiative AGN are often FR2 class AGN, while the kinetic AGN are often FR1 AGN. So this tree diagram can summarize all the AGN possible that is observed so far. So first, we have discussed so far all the radio loud AGN. So we have radio galaxies, blazars, FR1, FR2, FSRQ, and etc. We have another type of AGN called radio quiet. So it has a lower luminosity in radio spectrum. So this consists of quasars and Seyfert galaxies. So there are still many unanswered questions on AGN. So first, why jetted AGN are minority? We observe that the jetted AGN are not that abundant. We don't know the reason for it. And when we do find the jetted AGN, they often cluster to each other. Why? We also don't know. Next, we don't know the chemical and the physical property of the accretion disk. This may explain the energy output, the radiation that is emitted from the radiative mode AGN. And last but not least, is there a connection between the history of the accretion disk of the black hole with the history of the star formation in host galaxy? We want to know if there's a connection in the accretion disk so that we can infer the star formation history that could answer the galaxy evolution overall. So that's all from us. Thank you for listening in. If you have any question, feel free to ask. Thank you.